This is TWIS, This Week in Science interview episode, recorded on Wednesday, February 5th, 2020. How do climate models work? I'm Dr. Kiki, and today I'm going to fill your head with hot models. But first, thanks to the Burroughs Welcome Fund and our Patreon sponsors for their generous support of TWIS. You can become a part of the Patreon community at patreon.com/thisweekinscience.
I've got the kind of mind that can't get enough. I wanna learn everything. I wanna fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I wanna know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Welcome to another episode of This Week in Science. Today I'm speaking with Zeke Hausfather, a climate scientist and energy systems analyst, about his recent paper that looks at how well models of climate change have performed in their predictions of reality. In other words, checking to see if models have gotten anything right about global temperature and atmospheric carbon dioxide levels. Because really, what good is a model that doesn't get anything right? So as we jump into the show here, I want to remind you that you can tell your friends to subscribe to the TWIS podcast on iTunes, in the Google Play podcast portal, Stitcher, Spreaker, Spotify, Pandora, and TuneIn. You can also tell them to find us on YouTube and Facebook by searching for This Week in Science or just visiting twis.org. But now it's time for our interview. Welcome to the show, Dr. Hausfather. How are you doing today?
It's great to be here.
It's wonderful to have you here on the show. I was wondering how you got interested in not just the climate science area of work, but the analyst side of things. How did that come to be?
So I actually spent about a decade in the tech startup world. I helped start a couple energy efficiency companies, including Efficiency 2.0. I was the chief scientist of a company called C3. A lot of time analyzing how best to help people reduce their energy use to reduce greenhouse gas emissions. But eventually I realized my true passion was climate science. I had been doing it sort of as a hobby for many years, which is a strange hobby to have, but publishing academic papers, going to conferences in my free time. And eventually took the plunge, went back and got my PhD, and now do climate science as my primary thing, but still a fair amount of energy modeling work as well, because the two are very intertwined.
And you do a lot of writing also. I see that you have been writing on your analyses of climate science for a few outlets, and in addition to your research.
So I feel like you can do the best science in the world, but if you can't explain it to a large audience and can't get it well understood by people, it's not that useful. And so I've always focused a lot on communicating the science as well as doing the science. And so working with groups like Carbon Brief, like Berkeley Earth, and my current primary position at the Breakthrough Institute, I do a lot to both do research and to communicate the results.
The communication of climate science is one of the most essential communication needs we have these days. And it's also not one of the easiest, considering the environment you're communicating within, how it's received very often. So thank you for continuing to try to do that and for coming to join me on the show today. I want to get started now that I found out a little bit about you with the basics. Your paper that I wanted to talk about came out back in December-ish, and it looked at the climate models going back to like the 1970s and compared them against basically how things have turned out. Were the models good? Can we start with the question of what is a climate model?
Sure. So a climate model, contrary to popular assumption, is not simply, fitting a curve to past temperatures and predicting what will happen in the future. Climate models are immensely complex physics-based models based on basic physical principles: conservation of momentum, conservation of energy, very basic fluid dynamics laws, and thermodynamics laws. And essentially, how climate models are built is you take all of these physical processes and you put them into a spatial model of the world, where you divide up the whole world into boxes. Those boxes both go laterally, so latitude, longitude, and then up into the top of the atmosphere from the surface, and then down to the bottom of the ocean from the surface. And in each of those boxes, a ton of physical equations are being solved based on what's happening in the surrounding boxes, based on sort of the external forcings to the system, the amount of sunlight coming in, the amount of heat leaving. And out of that comes a lot of the patterns of weather that we see in the real world. And so weather models and climate models are actually very closely linked in their development. But with climate models, essentially what you're doing is you're taking a weather model, but you're running it instead of for a single day, you're running it for hundreds of years and slowly changing external forcings like CO2 to see what happens to the system.
Got it. And so it's basically the weather models are short term, whereas climate models are over longer terms.
Yeah. So a good analog to that is, it's hard to predict the weather past 7 days out, right? If it's going to rain or not, because, there's a lot of short-term variability and chaos in weather systems. But at the same time, we can always predict that next winter is going to be colder than this summer. And the reason why is because of shifting amounts of solar energy reaching the Earth. And so it's an external forcing, like the amount of solar energy reaching different parts of the Earth, that is what climate scientists are looking at. CO2 kind of acts in similar ways by trapping heat in the Earth system. And so we can look at the effects of those changes over long periods of time.
And this word forcing that you're using, I just want people to understand exactly what that means. Is it like a theoretical force, but it's as if you were pushing on a box to push it across a floor? It would be, is this how the sun's energy forces a change?
Sure. So when we talk about radiative forcing, which is kind of a technical term that climate scientists love to use, we essentially mean how much heat is being trapped in the Earth's system. Because right now, the sun's heat, shines down on the Earth. A fair amount of it is reflected back to space, but some is absorbed by the surface and various levels of the atmosphere and is re-radiated as heat. And that heat then escapes back up to space. Now, over the long term, the Earth tends to be at something of an equilibrium, right? The amount of heat coming in from the sun is balanced by the amount of heat leaving, and the temperature doesn't change. But if you suddenly change the amount of heat that can leave the system by, say, adding more CO2 to the atmosphere, you have a period of time where the Earth is out of equilibrium, where there's more heat, or there's more energy coming in than there is leaving. And so that's why the planet warms. And so radiative forcing unit we use to measure that energy imbalance, the amount of heat that's being trapped.
When I think of the model of the climate, it's like, okay, sun's energy coming in, there's a few clouds in the sky, some of them are reflecting light, some of them are keeping light trapped in. We've got the greenhouse gases that are bouncing light around and making it stay within our atmosphere, energy stay within our atmosphere, so things heat up. What other factors, are involved in creating a climate model? How do you go from a simple model of the climate to what we're probably dealing with now that seems to me completely overwhelming?
So when climate scientists were first starting to create physical models of the climate, they were starting with very basic models like you were just describing, simple sort of energy balance models where you have, the Earth is a black ball, for example, or a ball with a thin atmosphere. And as you go to more complex models, you add more and more processes to that. These days, climate models are run on the most powerful supercomputers in the world, and they take years of runtime to generate a full set of outputs across all the experiments they do. And the reason is because, a lot of complicated stuff happens in our atmosphere. Clouds form and they pass from one location to another. Precipitation happens, evaporation happens. Precipitation is in rain in some areas, snow in others. The height of clouds in the atmosphere affects whether they trap more heat or reflect more sunlight back up to space. There's little particles like dust and aerosols in the atmosphere that both can reflect incoming solar radiation or trap outgoing heat or serve as condensation nuclei for clouds. So it can be easier to have clouds if you have a lot of dust in the atmosphere. Yeah. And so those are just a few of the processes. There's sea ice, there's land ice, there's vegetative processes. So these days, climate models are not just climate models. We call them Earth system models, because in addition to modeling the atmosphere, they're also modeling ocean chemistry. They're modeling ocean circulation. They're modeling vegetative growth and decay. They're modeling carbon uptake and cycling by the land. They're modeling increasingly things like permafrost and how that's changing over time. And so there's thousands of variables that are being calculated every hour for hundreds of years of simulation at fairly high resolutions. And it's a lot. And it's impressive now. If you look at some of the higher resolution climate models, you see weather patterns, you see clouds going by, you see hurricanes forming that really look like you could be looking at a satellite image of the Earth from space. The advances in this field and the advances in numerical modeling of climate has really been amazing in the last 30 years or so.
So let's talk a bit about the looking at climate models and actually seeing how well they are simulating and how well they're predicting. How did you go about doing that, and what did you find?
Sure. So the challenge of evaluating climate models is that, particularly with climate models that are coming out today, we can't necessarily predict the future and then look to see what happens if we just published the model last year, right? It's not enough time for climate signals to emerge above the weather noise. The way that we evaluate modern climate models is what's called hindcasting, where essentially you look at how well the climate model predicted the past. How did it do from 1850 through today in predicting the Earth's warming compared to what actually happened? How did it do in predicting precipitation extremes in Australia? How did it do at predicting flooding in Louisiana? You can do all those sort of experiments on modern climate models. But the problem is those aren't always completely independent from the parameterizations of the models. Climate models still have to be tuned a bit by researchers because some processes, such as dynamics of cloud formation, occur at scales small enough that they can't emerge just from the physics. If you're looking at a climate model that has, say, a 25 kilometer by 25 kilometer resolution for its grid cells, clouds are much smaller than 25 kilometers. And so you need a certain amount of physical parameterizations to deal with these subgrid processes in the models. So that's a complicated way of saying essentially that because there's still some tunable parameters, looking to see how well climate models predicted the past is a good way to evaluate climate models, but it isn't necessarily the best way. What we really want, what the gold standard of prediction is do you effectively project what happens in the future, out of sample, so to speak, even though climate models aren't curve fitting exercises. And so what we decided to do with this paper was, in part because there were all these complaints, often with very limited evidence, that climate models always projected too much warming. We figured, well, let's go back and look at all the climate model projections that were ever published that we could find, from the first one published in 1970 through to ones published in about 2001, because after that, it's such a short period of time, it's really hard to evaluate how they did compared to the real world. And so we identified 17 different climate models. The early ones were like your basic diagram, very simple energy balance models. The later ones were fully coupled climate models, similar, though not quite as advanced as the ones we have today. And we looked for each of those models, what did it predict after it was published, and how close have observations been to what the model actually predicted. Now, the problem with that approach is that climate modelers or climate model forecasts are based fundamentally on two different things. One is the physics of the climate model. So if you add a certain amount of CO2 to the atmosphere, how does the temperature respond? That's determined by the model physics. But the second is how much CO2 do you add to the atmosphere? And that's not a question of physics. That's a question of economics, of public policy, of energy prices. If you're trying to predict in 1970 how much CO2 will be emitted in 2017, you need a crystal ball to get it right. No model in the world is going to tell you that. And so we really wanted to try to disentangle those two sources of bias. We didn't want to penalize a 1970s climate model that got the physics right, but might have gotten future CO2 quite wrong.
Right, because it's predicting different economic models or commercial industrial scale models because of they don't read the future for that.
Yeah. Well, and in the early days, these days there's this whole big set of collaborations between all the world's energy systems modelers and all the world's climate modelers. But back in the 70s, there's none of that. Back in the 70s, it was a single climate modeler who had built the model saying, let's just assume CO2 increases by 1% a year for the next 50 years and see what happens, right?
Got it. Yeah. Okay.
They don't necessarily think that's going to be right. It's just, a guess.
Right.
And so when we decided to evaluate these models, we really looked at it two different ways. One is a very simple, how did the model compare with observations for global temperatures after it was published? And for that metric, about 10 of the 17 models essentially got it right. They were statistically indistinguishable from observations after they're published in terms of the rate of warming. But we also, as I mentioned, wanted to correct for the fact that, a 1970s climate modeler didn't have a crystal ball as to what future emissions would be. And so we did another test where instead of just looking at the change in temperature over time, we looked at the change in temperature in the model to the change in forcings in the model. And again, forcings is essentially how much CO2 is increased and other greenhouse gases and things that affect the amount of warming. So what is the relationship in the model between the warming and the amount of forcing or the amount of CO2? And then we looked in the observational record, in the real world, what was the relationship between the warming and the amount of CO2 and other forcings. And we can compare those two values. And that's, in our paper, is what we called the implied TCR, which is a wonky acronym for transient climate response. But essentially, it's just how much do you warm if you increase CO2? And so by comparing the amount you warm for increasing CO2 between the observations and the models, we could essentially account for the fact that the models might not have gotten future CO2 right. And when we did that, we found 14 of the 17 models were pretty much indistinguishable from observations after they were published in terms of how much warming they projected. Of the ones that got it wrong, 2 were too high, 1 was too low, but there wasn't really any consistent error in the models. And so, this really increases our confidence that, at least for global average temperature, which in some ways is the easiest thing to predict from a climate standpoint, the models are really getting it right.
And so in your mind, the models are getting it right from, the data shows the models are getting it right. Yet there's this big question, like in the last week, there have been people talking about models like the NCAR climate model that started running hot last year. And there's, the bunch of headlines that I've seen saying climate models are running hot. What can we tell people for, I guess, the recommendations from the models and putting those recommendations into public policy? How do we adjust our efforts moving forward? Where are we headed currently, and where should we be heading?
So the models running hot is a couple different stories that we can dig into if you want. But more broadly, right now, the world continues to emit greenhouse gases at an increasing rate. Last year, we set a record for the highest greenhouse gases emissions ever. We set a record for the highest greenhouse gas concentrations ever. Yeah. And that record has been set almost every year, unfortunately. And as we continue to do that, we're going to commit the world to more and more warming. So right now, if we leave emissions at current levels, we're on track for somewhere around 3 degrees centigrade warming above pre-industrial by the end of the century. If we continue to increase emissions, that could be closer to 4 degrees warming. What we really want, and what the international community in almost every country in the world has agreed to, is to try to limit warming to below 2 degrees centigrade. And when we talk about these global average numbers like 2, 3, or 4 degrees, it doesn't sound like that much, especially to Americans who are used to thinking about things in Fahrenheit. So, double those numbers in your head to roughly convert. But even then, the global average, no one lives in the global average. In fact, most of the world is oceans, and the oceans warm a lot slower than the land because a lot of the heat that gets absorbed by the oceans gets transferred into the deep ocean. So the oceans are essentially a giant heat sink. And if you look at how the world is warming, you find that the land is warming about 40% faster than the oceans. So 3 degrees of warming globally is actually a bit over 4 degrees over land areas where most people live. And some parts of the land are warming much faster than others. The Arctic is warming twice as fast as the world as a whole. So 3 degrees of warming globally means 6 degrees centigrade of warming for the Arctic, or 10 to 11 degrees Fahrenheit warming for the Arctic on average, which is a huge difference to the climate there. So we're not talking about small changes by any means, and these changes will have huge effects on ecosystems and on human systems.
It's going to be absolutely massive. When a lot of people, there are people in the world who debate the merits of climate models and debate their usefulness. Do you think studies like the one that you've done help to bolster the communications response to those kinds of climate model naysayers?
Yeah, I mean, climate models are useful. All models are wrong, but some models are useful is a great phrase. And it's true. Climate models are never going to be able to perfectly simulate every single part of the Earth's climate. It's too complicated. But the fact that they've done such a good job over the last 50 years of predicting what actually ended up happening should give us confidence that, the basics are being gotten right by these models. Particularly in the 1970s, when the earliest models were published, most scientists at the time thought the world was actually slightly cooling. The reason why is they only had a very limited set of observational stations, almost entirely in the mid-latitudes in the Northern Hemisphere, which was experiencing a slight cooling phase. And so for scientists to come about and say, hey, we actually think this cooling is going to reverse and the world is going to warm by, 0.8 of a degree or 0.8 C, 1.5 degrees Fahrenheit in the next 50 years was a pretty radical pronouncement. It's not like today when you can say, oh, it's just going to keep warming at its current rate. You'll probably be pretty right for the next few decades. The fact that, these scientists were willing to make a claim at the time, 50 years ago, that things would dramatically change, and it did, really shows the power of these models. Now, it's important to mention that there still are large uncertainties going forward, right? Some of the models say, given current emissions, the world will warm 3 degrees. Some say it'll warm 2 degrees. Some say it'll warm 4 degrees. And so there's real uncertainty in how sensitive the climate is to CO2. And a lot of that depends on things called feedbacks. So as the world warms, what happens to snow? What happens to permafrost? What happens to the amount of water vapor in the atmosphere? What happens to cloud formation in particular? And there are uncertainties there that can lead to, a 2 degree or a 4 degree warming for the same amount of emissions across the different models. And that's an area where climate scientists are working on better understanding, narrowing these uncertainties. But all the models predict the world is going to warm if we keep, emitting greenhouse gases. There's really almost no uncertainty on that subject in the scientific community.
Yeah, and how much can we know about how much methane and other gases are contained in the permafrost exactly, and how fast that will be released, or how quickly greenhouse gases will be released from clathrates from the bottom of the ocean? Or do we have specific estimates of these things, or are a lot of these things still ballpark guesses?
I mean, we know a lot more than we did 10 years ago, and we'll know a lot more in 10 years than we do today. There's thousands of scientists around the world looking at each of these questions very intensely, in part because they are so important. The one thing that we can say is that, and this is an area where there still is a lot of scientific debate, but at least in the world of climate models are pretty linear. That is to say, the more greenhouse gases you add to the atmosphere, the more the world warms, the worse it gets. But in most cases, there's not some point at which you pass where things like spiral out of control and the Earth becomes Venus, the oceans evaporate. That sort of thing doesn't happen in models. And we're pretty sure it doesn't happen in the real world. At least there's very few, or there's no real analogs in the Earth's history that we can point to for something like that. But at the same time, there are periods in the Earth's past where there have been changes that are a lot larger than we'd expect, based on what we think happened in terms of greenhouse gases or volcanic eruptions or changes in the Earth's orbit. And so there certainly is reason to be worried that, there might be points that once we pass, we could see an exacerbation of warming. We could see the Earth move potentially even to a long-term warmer state than it is today. Those are probably not like literally end of the world type things. But there's certainly things that keep a lot of scientists up at night.
Yeah, a lot of scientists. I mean, there is the argument that, the Earth will go on. Life on Earth will continue to thrive, but it may become a situation that is very difficult for humanity to continue in the way in which we are used to, right? We don't know where it's going to go, and maybe it's best to hedge our bets in a bit of, I don't know, amelioration of trying to fix some of these.
I certainly don't think we should burn all our coal just to see what happens.
Oh, come on.
That's not going to be a.
Come on, we have an N of one. Our Earth experiment.
It would be a great science experiment, but it wouldn't be great for humanity.
Exactly. Yeah.
And I think there's also an argument to be made that the natural world as we know it is probably in some ways more vulnerable than humans, right? Humans are adaptable, particularly when they have time and resources to do so. Humans live in the Sahara, humans live at the Arctic Circle, but a particular species of tree rarely lives at both the Sahara and the Arctic Circle. And so the rate of change right now is happening so fast that a lot of ecosystems are having trouble adapting. If we continue pushing it, a lot of human systems are going to have trouble adapting too. But it's the natural world that really shows the first really big effects of climate change.
And I can't, not just resources and time to adapt, but also I think for humanity, it's the ability to cooperate.
Yes.
To collaborate and cooperate, which I don't know. Let's see if we can get past ourselves and do that.
Yeah, the strength of our institutions, our society, our governments plays a huge role in our ability to adapt to a warming world, because we're going to have to adapt to some warming, right? The best case, it's only another half a degree warming. Realistically, it's probably at least another degree warming. And in the worst case, it's a lot more than that. And what's interesting is scientists have actually started looking a lot more at scenarios where the socioeconomics of the world look different, and to see how that affects the costs of climate change. In many ways, the worst case scenario right now is not the one where society is super rich and prosperous and burning so much coal to generate that prosperity that we get a ton of warming. That's not a good world. But the worst world is a world where societies are falling apart, where, regional rivalry, isolationism, nationalism is driving conflicts. The world remains unequal. Large parts of the world are very poor. You might have a little less warming in that scenario than one where, the economy is roaring and everyone is super rich and equal. But you have a lot lower ability to adapt to that warming, particularly for the large parts of the world that remain mired in abject poverty. And societies are a lot more vulnerable in that world to, climate shocks. Climate is in many ways a risk multiplier. It takes existing problems and potentially makes them a lot worse. And so the real nightmare scenario that keeps a lot of us up at night is not, what is the most emissions human could possibly have? It's, what would a world look like where both our societies are weak and it's getting a lot warmer?
I don't want to live in that world. Let's keep the lines of communication open so that people can so that we can help each other figure out how to avoid that future.
We actually have an acronym for that world that you'll probably hear down the road, but it's called SSP3. Stands for Shared Socioeconomic Pathway 3. Is the real worst case.
Is this kind of analysis of the Earth system, not just the climate model system, but the Earth system modeling with society layered into it? Is that a part of the IPCC and also the conversations that are taking place on a global level between countries? It
is, though I should be careful to describe exactly how these models work in that way. Yeah. So climate models started as atmospheric models, then they integrated oceans, then ice sheets, and more recently, what's called biogeochemistry. So carbon cycles, vegetative cycles, modeling trees, things like that. That's kind of the state of the art for physics-based climate models or Earth system models today. At the same time, there's a parallel literature of socioeconomic and energy system modeling. And right now, those socioeconomic and energy system models mostly feed into the climate models.
Got it.
People are trying to move toward going forward is to couple those two types of models. So not only would the socioeconomics and the energy system determine how much emissions that the climate model uses to predict warming, you then take those warming estimates and feed them back into the socioeconomic model to figure out how it affects, the economy, how it affects emissions going forward. Because arguably, you could have a world where, climate damages get so high, they actually reduce our ability to emit more CO2. And that sort of thing
that.
isn't modeled today.
Yeah, I mean, there are those potential outcomes where our industry, where people are affected so much that, oh, our societies aren't working, and so we're not drilling for oil, we're not mining for coal, we're not doing these things, or we can't afford the transportation to get food from one side of the country to another, or to drive our fleet vehicles between cities. All those.
But those aren't the type of negative feedback loops we're hoping for.
No, not at all. From a modeling perspective, and also from your perspective, working on this in this area, what do you think are the places that people need to focus?
So on the climate model side, there's a few large drivers of uncertainty. Probably the single biggest one is clouds. We don't have a great understanding of exactly how clouds will change as the world warms. And there's very different results and different assumptions across the different modeling groups. The 100 or so different models around the world that are used to project future climate. And so better understanding cloud physics is a huge, important thing to narrow the range of uncertainty in future warming projections. That's a big one. The second, which is strongly related to clouds, is aerosols. And so aerosols are these small reflective particles in the atmosphere. We have a good sense of how they scatter incoming sunlight, but we have a much poorer sense of exactly how they interact with clouds. So how they affect cloud formation and what types of clouds. And so those sort of cloud physics and aerosol cloud interactions are probably the two biggest remaining physical drivers for uncertainty in climate models. But beyond that, there's a lot of uncertainty once you get outside of temperature that we could do a better job addressing. So climate models, for example, don't necessarily agree with each other very well on average precipitation changes. So if you look at where I live in Northern California, about half the climate models say it's going to get wetter in the future. About half it's going to say it's going to get drier. They all say it's going to get warmer. That's not in question. And so things like that, once you get out of temperature to some of these other climate variables, there are larger amounts of uncertainty and a lot of additional sort of physical modeling that could be improved there. And then on the energy side, there's been a big push recently, including a comment that I published in Nature last week, to try to get a better understanding of the likelihood of different future emission scenarios. So trying to figure out, where is the world headed with current policies today, and what might be a realistic worst case and best case from where we are today. A lot of the climate literature on impacts relies on a scenario that is very high emissions, and we argued at least that it might be too high emissions. It's a world where world coal use increases 500% above today's levels, and while that, yeah,
that's a lot.
That's a lot, yeah. And that didn't seem that crazy 10 years ago when these scenarios were developed, because China was adding a coal plant a day. Right. And renewable energy was 4 times more expensive than it is today.
Right. And now we've got solar panels picking up a lot of slack, and China is, instead of doing coal, they're doing nuclear, or they're investing in solar and wind and other renewables.
Yeah. So the world is slowly changing. It's not changing fast enough that we've actually managed to peak global emissions yet, or for that matter, decline them. We need to get emissions to zero if we want to stop the world from warming. But it's not accelerating as fast as it was before. We're slowly starting to bend that curve down toward, maybe a world of 3 degrees warming instead of a world of 5 degrees warming as a worst case. That's still not where we want to go, but it's better than where we could have been. Right.
I was talking with a woman who works in Antarctica, and she was talking about this whole situation. Basically, it's like you're at the top of a hill, and you realize your car is going to crash, and it's just a question of at what point do you put on the brakes? And that's kind of where we are now, starting to put on the brakes, hopefully enough to reduce the impact that we have at the very end.
Yeah. Well, we were going 70. Now we're going 50. We need to stop. And
we need to stop. Yeah.
We're slowing down, but not nearly fast enough.
Yeah. Over a decade ago, I had conversations with people a lot on the energy side of things about what was called the water energy nexus, and how water availability is also something that is tied into energy availability, and that in a changing climate, water becomes less reliable in some places. And so that's going to have an impact also. So once again, we get into situations of future modeling of possibilities that have lots of parameters that have to be taken into account. There's a lot of complexity.
Yeah, and certainly areas that rely on snowpack, for example, for hydropower and things like that. Those are not that hard to model, right? As it gets warmer, the snowpack's going to decrease. Though obviously, the devil's in the details for that sort of thing.
Yeah. What are you working on next, or working on now, that you can talk about?
So there's a couple interesting projects in the works. There's a big review paper on climate sensitivity. So essentially how much it's going to warm in the future if we keep increasing CO2. That's slowly working its way toward being published, where we're trying to narrow that range that's been, fiendishly wide for so many years. Though at the same time that we're trying to publish that, we have the newest generation of climate models, some of them coming out with very, very high sensitivities. So it's become a whole interesting debate about that. But apart from that, I'm working on a piece that'll be more of a public-facing communications thing on carbon cycle feedbacks. So explaining, as the world warms, what are the various estimates we have of how the permafrost melts, how the ocean carbon sink changes, how the land carbon sink changes, what is the uncertainty across models for those sort of things, and then what is the latest studies showing us. Because one of the challenges is those uncertainties are not very well taken into account today in the climate model results that most people use. The reason is a little complicated, but essentially about half of the climate models are not Earth system models. They're old-fashioned atmosphere-ocean models. And so they don't have the biogeochemistry in them to try to be able to, reflect carbon cycle changes. And so when we run these big model comparison projects for like the IPCC reports, we essentially give the models a set of concentrations of different gases like CO2, methane, nitrous oxide, et cetera, and let them, figure out how much warming that results in. But the models aren't, taking the raw emissions and deciding how much concentration of atmospheric concentrations that results in. And so a lot of carbon cycle feedbacks are sort of being missed in that process, or certainly the uncertainty in those carbon cycle feedbacks are being missed. So to better discuss that issue and try to capture those uncertainties. And then
make the uncertainties more certain.
Yes, make the uncertainties more certain.
Yeah.
And then I'm also working on a report on climate tipping points to better go through all of the climate tipping points that are commonly discussed in the media and give a better sense of like, what are the thresholds associated with those tipping points to the extent that we can tell? What are the timeframes over which they operate? Are we talking like a 10-year, 100-year, 1,000-year, a 10,000-year timeframe? And how reversible are they? If we bring temperatures back down to pre-industrial levels, can the ice sheets stop shrinking, or is there a point at which you pass and then you've committed yourself to loss? And so a lot of questions like that to better clear these up, because tipping points is an area that,
12 years. We have 12 years. That's what I heard last year. That's what the media told me.
So the one thing that we can tell you for sure is there's not a point of no return that like in 10 years we pass and suddenly everything spirals out of control, the world ends. Nothing in the science supports that. But there are ecosystem levels. If we pass 2 degrees, most of the coral reefs can't survive that temperature difference and die. That's a very well understood tipping point. Others are much less well understood. How the ocean conveyor belt will change as the world warms, for example. It's not going to shut down instantly. We know that. But is it going to slow by 10% or 50% by the end of the century, or 80%? We don't know that very well. How much carbon is going to come out of the permafrost? Is it a slow, gradual process, or are there some things that can trigger sudden releases that we have to worry about? And so all of those sort of things are what worry us, and what we're trying to better quantify.
That sounds like you have a lot of wonderful, important work cut out for you in the months ahead. Yeah, I mean, I'm just thinking about the tipping points and all these questions that you're bringing up. I've even had people ask them, and we don't know the answers to so many of these things, and the nuance I think it's important for people to try and understand, to know why people are concerned. Why there are so many people who are now really pushing for, like you said, zero emissions. Can we get to a point where we take it back and we can fix what we've done? But there are unanswered questions, and I'm really glad that people like you are working on this to help answer them. Yeah, go ahead.
I was just going to say that, science is all about uncertainties, right? If we knew exactly what was going to happen in the world, life would be a lot easier. But the problem with uncertainties is they cut both ways. It might not be as bad as we think it's going to be, but it also could be a lot worse than we think it's going to be. And so the more we can narrow those uncertainties, the better we can plan as a society for what we need to do.
Yeah. Yep. The more, what is it? I think it was Rumsfeld who was talking about the known knowns, the known unknowns, the unknowns, the unknown unknowns, all the things. Can we start determining all of them? Do you have, if you were to have one message for people about climate models and how to talk to others about climate models and about climate change and what would you tell them?
So, climate models are very useful tools, and they show, a range of possible things that might happen in the future. But at the end of the day, the fundamental physics doesn't rely on complicated supercomputer models. When it comes to climate, the things we know for sure, that the whole scientific community agrees on, is that the world is warming, that atmospheric greenhouse gases are increasing, that greenhouse gases trap heat, that humans are causing the increase in greenhouse gases, and that humans are causing the Earth to warm. There's plenty of debates about the minutiae, or about how well this model did or that model did, or, is it going to be 2 degrees or 4 degrees by 2100? But those don't really change the fundamental debate, and they don't change the actions we need as a society to take. As long as we keep emitting greenhouse gases, the world will continue to warm. And eventually, we as a society need to cut our emissions down to zero. And, we're starting on a long path to do that, with, falling prices of clean energy, with things like electric vehicles, with energy efficiency. We know broadly as a society what we need to do. The challenge is both to get the costs of alternatives down far enough and to get the political will to deploy them.
Awesome. Thank you so much for joining me today. It's been wonderful getting to speak with you. Is there a place where people can find you, where they can find out more information about this and other work that you do?
Sure. So they can follow me on Twitter. That's probably the best way to get up-to-date stuff on what I'm working on. My Twitter tag is the first 8 letters of my last name, just Hausfather.
Hausfather. Okay. We'll have a link.
I made it back in the early days of Twitter before I realized it was going to be a bigger thing. And anyway, beyond that...
Now you're stuck with it. There you go.
Now I'm stuck with it. And then beyond that, they can follow a lot of the popular science writing I do on a website called Carbon Brief, which is a UK-based nonprofit organization that focuses on communicating the nuances of climate science and energy stuff to a broad audience.
Fantastic. I think that will be of a lot of interest to people in our audience. Once again, thank you very much. And everyone, thank you for listening to this interview. I hope you enjoyed the show. And if you did, share it with a friend. That would be fantastic. I want to give some shout outs to people who help the show. Fada for your help with social media and show notes. Gord for manning the chat room for our chat room moments. Identity4 for recording the show, for the audio for the podcast, and our Patreon sponsors. I'd also like to thank the Burroughs Welcome Fund for their generous support. You can find information about Patreon at patreon.com/thisweekinscience. You can catch our regular Wednesday broadcast on Wednesdays at 8 p.m. Pacific time on twis.org/live. Show notes and links are going to be available at our website, twis.org. You can contact me directly. Kirsten at thisweekinscience.com is my email. Put TWIS in the subject line so it doesn't get spam filtered into oblivion. You can also find me on Twitter where I'm at Dr. Kiki, or you can get TWIS at TWIS Science. TWIS Science, all one word. We love your feedback, and I hope that you'll join us again for more great science news and discussion. And if you've learned anything from the show, remember, it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand.